Hello and a warm welcome to everybody. We would love to wish everyone a good morning, a good afternoon, or a good evening, depending on where you are in the world today. My name is Jamie, and I'm one of the co-founders of Safopedia. Today, we're very proud to present Hazardous Materials. Is your chemical storage solution compliant? This Safopedia webinar is being presented by U.S. Chemical Storage, a Just Right Group company. It is now my pleasure to introduce to you today's presenter, Fred Romig. Fred is a hazmat consultant with U.S. Chemical Storage. His experience in the hazmat industry spans several decades, as he made a name for himself by developing hazmat storage buildings with unique features that customers wanted, but nobody provided. By defining best practices in the design, manufacturing, and on-site installation of chemical storage buildings, as well as utilizing a consultative approach, Fred provides customers with peace of mind through the entire process. He is well versed in local, national, and international codes and uses the information to craft relationships with all different types of people involved in the industry, from architects to engineers, fire departments to code officials, and ultimately with the end users. Fred also has a knack for solving real problems for customers. His exploration into new approaches has resulted in a number of inventions and 8 patents. He graduated from Youngstown State University with a degree in business administration. I now invite you to sit back, relax, and enjoy the presentation. With that, Fred, please take it away.
Thank you, sir, and welcome everybody to this good presentation that's forthcoming. I want to say that I have my departed wife to thank for me being the person giving this presentation. You see, years ago, I was sending out resumes and asked her if I could waste one on a job that I saw advertised in the paper for some sort of manager of hazmat buildings. I wanted to find out what a hazmat building was. I had no idea. She said, okay. So I got the expected turn down letter, and while reading it, my wife Connie said that the envelope was more important to pay attention to. I didn't believe her, but eventually I see that she was right. It had a sticker announcing that the company would be at a hazmat convention. And she said if I was as good as a talker as I like to think I am, that I could talk my way onto that convention floor and get an interview, which I did. And I was told at the end of the interview that I was to be invited out to the factory on the following Monday. And so I worried for a while because I thought he's going to find out that I'm not one of the remaining contenders for this job. But I showed up on Monday morning, and he came to the door and said, well, he said, I'm sorry, but I'm so busy. He said, would you come back next week? So I had to sweat another week thinking he's going to find out that I really shouldn't be there. But anyway, I showed up the following Monday. And he invited me in very friendly and led me to the conference room, sat me down, and said that he would be back. Well, he took a long time. And when he did come back, his Irish was up. His name was Doherty, so he was Irish. He was red-faced. He slammed down a stack of resumes and said, where do you get the balls to pull a trick like this? I told him he had to ask the 6 remaining candidates what they would do when their sales proposals were turned down. I told him I didn't have to do that because he already had my answer because I just demonstrated what I would do. He got up, left the room, he brought his wife back in, and we together proceeded to sell her on offering me the job. So I have my wife to thank for being here. So here's what we're going to talk about today. We're going to talk about how to keep our environment, employees, and facilities safe regarding hazardous chemicals. To talk about all types of facilities that exist above or below ground in industrial, institutional, or commercial settings is too big of a task for this presentation. So we're going to whittle this thing down. We're going to focus on a single, unique structure that, for the most part, has more stringent code requirements. We're going to discuss why a hazmat chemical building, regardless of its contents or use, is probably the safest building on any industrial site. This is because it's constructed to meet or exceed tougher specific codes. What is a hazardous chemical building? A chemical building is designed to protect property and employees from fire and explosions while storing, mixing, dispensing, testing, and handling hazardous materials, especially flammable and combustible liquid chemicals. Chemical-related accidents do happen on industrial sites. Many, as you know, the Occupational Safety and Health Administration, that's OSHA, O-S-H-A, was created to protect workers from such accidents. The Environmental Protection Agency, that's the EPA, was established to protect our environment. Prior, more than 100 years of codes were pulled together by thousands of highly educated, trained, and experienced committee experts from the equipment, manufacturing, enforcement, insurance, safety, research, and other related fields. Why? Why? Because millions of dollars went up in smoke as property were damaged or destroyed, and lives were lost, and workers, many, disabled. All because there were not enough standards, or if there were, they were ignored or were not strong enough or nor enforced. This is a serious business. Now, prior to OSHA and the EPA's foundation, the National Fire Protection Association, that's NFPA, and the National Building Codes Association, that's BOCA, B-O-C-A, was established earlier around the turn of the 19th century. These organizations have instituted codes that define requirements for chemical building construction that meet minimum strength, fire, and explosion standards. NFPA and BOCA were founded and have been the foundation for the international codes that have come much more recently. These codes have limited the total footprint of a chemical building not to exceed 1,500 square feet. Yet, the largest one ever built was 3,182 square feet per floor, shipped in 24 modules for the General Motors powertrain division. This was due to the relationship the user had with the local authorities and are self-insured. This was utilized for testing large truck engines and their transmissions. Now imagine the amount of codes that had to be considered in getting this building approved. These codes were established from trial and error experiences and results from all types of disasters and scientific testing over 100 years. Here's an example, as you see, of one building moving slowly, making a very tight turn onto a bridge in a small rural town with an escort car out in front. The turn was complicated because the building was 72 foot long and 12 foot wide. They had to remove posted signs even to get over the curbs. As for extreme dimensions, a building's height has caused the most trouble. For example, I know of an incident when an escort car with its steel height testing pole moved into the left lane of a dual highway while going under a bridge. But the tractor trailer, with its tall hazmat building, could not find a way through the traffic to follow the escort over into the next lane. The driver felt a bump and just kept going. A police car saw the sparks fly as the building's roof hit the bridge and then on down the road where the free tie-down chains clattered on the highway. The officer chased down the tractor trailer to inform the driver of what had taken place. The clearance under the bridge on the right next to the berm was inches lower than the clearance in the left lane next to the medium strip. So the car was able to get under the bridge, but not the truck. Some observers and the officers, they all get a good laugh recalling this story, especially the officer, because he was chasing that car and trying to avoid at the same time running over the chains for fearing what it might do to his vehicle. The shipping company paid more to repair the bridge than was the damage to the hazmat building because of how strongly they're built. This second photo of the long building shows a couple of cranes at the back of the client's main facility. These cranes are lifting the same hazmat building off the trailer, and it is about to place down on a concrete pad, pre-poured by the client. Now this next picture is a night shot of the front of the building. It may have been the first and could still be the longest single hazmat building ever built. And again, at 72 foot long, it has 5 separate rooms, 2 of which were flammable and combustible liquids, and the rest were for non-combustible storage. The design of a hazmat building must meet or exceed local, national, and international minimum and maximum thresholds. These include dimensions, strengths, roof snow accumulation loads, wall wind loads, storage capacities, fire and explosion resistant construction, alarm systems, and more. The building in this photo was called a tank farm. Here you are looking into the open top of the 2 lower modules already installed on the client's concrete pad. Using a crane, the client has placed 2 of their mixing tanks into the floor of the hazmat building. In the next picture, now the second of 2 upper modules is being placed in its proper location to complete the tank farm. To cap off these buildings' unusual dimensions, here is the tallest known chemical storage building utilizing 3 modules stacked on top of each other to make it 3 stories high. The 8-foot high lower level was for storage, and the upper 17-foot high level was for experimental testing. Keeping your environmental safe. Now I'd like to get into 2 unique features having to do with hazard chemical buildings. These exclusives are spill containment and low-level ventilation systems. We will include fire suppression as a third topic. Keeping your environment safe via spill containment. A chemical storage building's most unique feature is that it must have a liquid-tight sump built into the floor. Sumps are constructed of either continuously poured concrete curb integral to the concrete floor or a continuous welded 10-gauge steel plate for sump walls and floor. Next slide. The idea is to catch spills and keep them from getting into the soil under and or around the building. Just how much containment is required, or how high does the sump walls have to be? OSHA Code paragraph 1926.152 requires a 4-inch sump depth or height when a fire sprinkler system is installed. Now this is silly because not all hazmat buildings are required to have sprinkler systems, such as for non-combustible chemical liquids. The EPA Code paragraph number 20 CFR 264.175 requires a sump capacity to be 10% of the total of all the containers stored in the building, with or without sprinkler systems. A more practical answer. Common sense and being practical is also required. If the containers are sitting down on the sump floor, then the amount of sump capacity or its wall height must be increased by the displacement factor of the total number of the stored containers. If the containers are placed on an elevated floor, then any of the support structure involved in the elevated floor's construction is also to be considered for its displacement factor. In the late 1980s, Factory Mutual, and that's known as FM, was brought into the picture because hazmat building manufacturers wanted a qualified third party to review building designs. This qualified their proposals to prospective clients that their building met certain safety codes, especially the National Fire Protection Association NFPA 30, which is called the Flammable Combustible Liquids Code. This is the only code with a simple chapter devoted to factory-produced steel chemical hazardous buildings, listing all required elements. But it lacks details. For example, to find out how low a ceiling can be, it's not in NFPA 30. You have to refer to OSHA Title 29, paragraph 1910.37I. It says the distance must be 7 foot 6 inches from the chemical storage building's elevated flooring to the finished ceiling. Even though NFPA 30 agreed with the EPA, FM, on their own, raised the sump capacity from 10% to 25% of what's stored. For storage of common 55-gallon drums sitting on an elevated floor results in the sump floor wall having a minimum height of 6 inches. You can begin to see why knowing what's in what codes is very important. Other factors must be considered that determine sump floor height. If there is a water-based fire suppression system, the capacity of the sump height must add in the total amount of dispensed water in a 20 or 30-minute deluge. This is dependent on local codes and or opinions of the local authorities having jurisdiction. And this is because the spilled chemical usually will not mix with water but will float on the surface of the rising sprinkler water. This cannot be allowed to pour over the door sills, out of the building, and into the environment. The calculated water catch will result in sump heights usually greater than 20 inches. The sump floor may be sloped. If the slope is 2 inches from the high to the low spot, the total sump height needs another inch. Sloping the sump floor allows for easy drainage during sump cleaning. There may be a lot of dirt tracked into the building over time that needs to be cleaned periodically. A spill is required to be cleaned up immediately. The slope should flow to a slope trench for faster drainage and places the buildup under the aisle of the elevated floor, which is usually made of grading. If the chemical on the surface of the water catches fire, it will not be cooking the bottoms of the remaining containers on either side of the aisle. The fire will be exposed directly to the fire suppression system that would be on the ceiling. Keeping your environmental safe, this time we're talking about ventilation systems. The second most unique feature of a chemical building is its ventilation system. It is upside down as compared to familiar systems designed to remove hot air buildup at ceilings and from attics. During a spill, flammable combustible liquids will flow down through the elevated floor to the bottom of a flat sump floor, spreading evenly all over the building. This provides the greatest surface area for evaporation, which will create the fume. Immediately after a spill, the liquid is exposed to the air. That's even before the liquid even hits the floor. Evaporates and becomes a fume or vapor. This fume is usually heavier than air and will drift down, adding to the total fume accumulation across that flat sump floor. The fumes will begin to rise upward past the elevated flooring. If the fume-air mixture reaches a particular percentage depending on the chemical, it is susceptible to ignition by flame or spark. If ignited, an explosion in the building will occur. Ventilation is a solution. NFPA 30 Flammable Combustible Liquids Code, paragraph A-4-6 says simply, quote, Ventilation requirements include mechanical ventilation where dispensing operations are expected, unquote. We'll talk more about the different types of ventilation systems on the very next slide. There are three types of ventilation systems. There's gravity ventilation. A single opening in the lower wall of the building is fitted with a rain louver and a bird screen. Now, if it's a fire-rated building, they add a fusible link drop-down shutter. Now, this acts as a vent. The top of the rising fumes will be pulled out of the opening by gravity like a hole in a coffee cup, allowing the fume to drift down on the ground where it eventually dissipates into the atmosphere. If there was another vent, like the first one on the opposite wall, the wind outside the building can push fresh air in and or pull out the fumes outside. This is the least expensive and least dependable method. Then comes natural ventilation. Now this starts with the same single low-level vent just described, but the second vent is placed high up on the opposite wall near the ceiling. This expels hot air near the ceiling, but near the floor, under the upper vent wall, for more than a half of the building, the fumes remain. This is a cheap solution and does not do a good job of expelling heavier-than-air fumes. Now we'll talk mechanical ventilation. It starts again with a low-level vent becoming the air intake, and the second low-level vent on the opposite wall acts as an output, similar to the gravity ventilation solution we already talked about. Here, outside the second vent, has installed a vertical stack or duct up on the exterior wall. The fan, per NFPA 30 paragraph 18.5.5, shall provide 1 cubic foot per minute of exhaust air for each square foot of floor area, creating a negative pressure in the room. This comes to over 6 air changes per hour. The International Fire Code, paragraph 2704.3 says, the fan is to run continuously, have a break glass shut-off switch, and an exhaust vent located within 12 inches of the elevated floor. The exhaust air shall not be recirculated back into the room. In addition, it is important to know how the exhausted fumes mix with the outside air. NFPA also says the fume discharge shall terminate above the roof. Now, when a chemical storage building is installed inside a larger building, the fan must be installed on the roof or wall of the user's building. Negative pressure must be maintained all the way from the chemical storage building through the duct to the fan. If the threat of an explosion is high, and or to avoid installing explosion relief, it is permitted by meeting the requirements of NFPA 69, paragraph 3.3.3, quote, ventilation or air dilution, end quote. Paragraph 3-4.1 adds, quote, suitable instrumentation shall be provided to monitor the control of the concentration of combustible components, unquote. And 3-4.3, quote, alarms shall be provided, end quote. Now, what has been accepted is having dual or secondary fans operate as an emergency backup or redundant system. The fan number 1 would run continuously by adding gas sensors that monitor concentration for gas alarm and a sensor that monitors air pressure in the exhaust stack for the number 1 fan gets a fan malfunction alarm. The gas alarm will turn on the second fan to increase the air intake. The fan malfunction alarm would also turn on the second fan to maintain the air intake. When needed, an emergency standby generator would provide power for this dual fan system, or it would be connected to the main facility's emergency power grid. This dual fan system would never allow a flashpoint mix of fume and air to occur. So, even if someone was to light a match, an explosion would not take place. Now here we have 4 photos. The one in the upper left-hand corner, there is a blue strobe on the roof edge for a fan malfunction alarm. The yellow strobe is for the sump spill alarm, and the red strobe for the fire alarm. There's also a single fan at the top of a single duct over a single exhaust vent. Then the photo on the right shows dual fans at the top of a dual duct over dual exhaust vents. In the lower left-hand corner, you've got an upper exhaust fan outside a vent opening. Inside the vent opening is an explosion-proof motorized louver. At a predetermined temperature setting, the louver will open and the fan turns on, pulling hot air off the ceiling. Supposedly a poor man's air conditioner. But in some cases, there are stored chemicals whose fumes are lighter than air, and a chemical temperature could trip their removal with this system. And in the last photo in the building on the right, you've got a couple of ducts that rise up from the exhaust vent opening up to the roof's edge and then over the roof's edge, and then the fan is mounted on top of the duct. Keeping your facility safe, now we're going to talk about fire suppression, which is our next topic. 2 of the most common fire suppression systems are water sprinkler and dry chemical. First, we'll talk water sprinkler. This type of fire suppression system was first used at the turn of the 19th century in the United Kingdom. The first automated system was installed in a factory in Connecticut in 1874. Water sprinkler systems are favored by almost all fire marshals. Basically, iron piping is installed on the ceiling of a chemical storage building where sprinkler heads are attached on the piping at predetermined spacing based on the known water pressure supplied by the local water company. Each sprinkler head has a fusible link with a set temperature setting and will automatically, individually, one head at a time, dispense the spray of water in a predetermined pattern. In a wet type, the pipes are full of pressured water. In northern and southern hemisphere freeze zones, care must be taken so the incoming water supply is buried deep below the local ground's frost line and insulated or wrapped in electric heat tape to prevent water from freezing. The wet sprinkler system requires the interior of the building to be heated in the winter. Or there's a dry type water sprinklers that have no water in the piping prior to discharge, just air. When a fusible link releases, the air comes out first, and then the water will be released from a heated nearby facility into the sprinkler piping. And you can see that in that lower left-hand photo that was up. Now there's dry chemical systems. A dry chemical fire suppression system, instead of a water-based system, has fire extinguishing powdered chemicals with added particulate material to provide resistance to packing, moisture absorption, and caking in the piping to achieve a proper flow. It extinguishes the fire by smothering and interfering with the combustion process. The powder mix is contained in a storage tank. This dry chemical, when released, is propelled by compressed CO2. The heads do not come with fusible links, as in the water sprinkler system. Within inches and parallel to the piping, a cable is strung on the ceiling from far within the building, running all the way back to the controls. On the cable, fusible links are distributed at predetermined distances in the cabling, so that when the temperature from a fire reaches the melting point of any single fusible link, the cable is cut. This will release the valve of the compressed CO2, pushing the dry chemical powder into the piping and out of all dispensing heads at the same time. Now, there is commonality with all fire suppression systems, and there's more than just sprinkler and dry chemical. But they're all common in that they can trip a fire alarm and turn on a local audible and visual alarm strobe on the roof, as we just saw, and send a signal to a facility's central guardhouse, and it can automatically, or they can manually send that signal on down to the fire department. Now, alarm can be used to close and unlock doors, shut down the ventilation system, release fire-rated drop-down shutters over non-fire-rated windows and non-fire-rated super-insulated cooler doors over non-fire-rated explosion relief panels, etc., etc. Fire suppression systems are involved in determining the amount of hourly fire rating of the construction of the walls and ceilings as to how close hazmat buildings are to other buildings, roads, and property lines. Codes written by NFPA, OSHA, and the International Fire Code all have very similar but not exactly alike on setting distances. For example, most codes require the building to be 4-hour fire rated when within about 10 feet of another building. But adding a sprinkler fire suppression system will reduce the fire rating to 2 hours. At the other extreme, a hazmat building more than 50 feet from buildings, roads, and property lines do not have to be fire rated or protected by a fire suppression system. So there you have had a brief description of hazardous chemical buildings. We have defined what a chemical storage building is and what makes it unique from other buildings. We have touched on what's expected for chemical spill containment, types of ventilation systems and their operation, plus 2 of the most used fire suppression systems. We've also discussed some of the codes needed to meet or exceed proper chemical storage. Other future topics for discussion are what building strength is expected if defending against explosions and how to determine the amount of explosion relief. Also, the design of explosion-proof interior and outdoor lighting, heating, and cooling components. They all have to be Class 1, Division 1, Group C and D explosion-proof. Another area of interest are the extreme locations where these buildings can be placed, from the desert to the Arctic. So, for example, I know of a hazmat building that was designed for extreme cold, had to be built in 2 modules to fit into a military C-130 aircraft to be flown to the island of Attu at the far end of the Alaskan Aleutian Island chain. That's it. I hope this webinar has helped with some of the general education and would welcome any questions. Thank you for your time. Jamie, I'll turn it over to you.
Great. Thank you, Fred. Really want to thank everyone for attending. We definitely know you have a choice of where to spend your time, so we're extremely grateful that you spent it with us. Thank you, Fred. Really appreciate your time as well.
It was a lot of fun. Thank you very much for asking.
Yeah, our pleasure. So thanks again, everyone. Take care and stay safe.